Seventh, Russell's paradox. Russell's paradox. First, let's understand what we mean by paradox. A paradox is a logical contradiction. A paradox is a logical contradiction in an argument. That is, yes implies no and no implies yes. Now, what does Russell's paradox state? Russell's paradox states that there is no set of all the sets. There is no set of all the sets. This is Russell's paradox. This is for the one who accepts axiom of regularity. This is for the ones who accept axiom of regularity. Later we have modify Russell's paradox. Modify Russell's paradox is especially for the one who are against AOR. Later or we have modified Russell's paradox. Modified Russell's paradox. Modified Russell's paradox states that there is no set of all the ordinary sets. This is for the one. This paradox is for the ones who are against AOR, axiom of regularity. Let's discuss again what we mean by Russell's paradox. Russell's paradox states that there is no set of all the set. This is for the ones who accept AOR, and modified Russell's paradox states that there is no set of all the ordinary sets. We have discussed what we mean by ordinary set before. So ordinary set means, let me write here, it's a set. It is a set that doesn't belong to itself. That is, X doesn't belongs to itself. This is ordinary set. So modified Russell's paradox states that there is no set of all the ordinary set. This is for the ones who are against AOR. Modified Russell paradox shorthand is MRP. Now let's discuss the proof. Now let's see the proof. This proof are for the ones who accept AOR. For those who accept AOR. Now let's start the proof. Let's define X. Let's define a collection X as set of all A such that A is a set such that A doesn't belong to itself. Let's define a collection X such that let's define a collection X as set of all set of all A such that A doesn't belong to itself. It's a collection of all the set that doesn't belong to itself. Hence, the X is the collection of all the sets. Now, if the collection X is a set, then this implies X doesn't belong to itself by AOR. Because if X is a set, then this implies X doesn't belong to itself by AOR, because according to axiom of regularity, the set doesn't contain itself. Then this implies X belongs to itself by the rule of collection. Here we have collected all the sets that doesn't belong to itself, and these elements belongs to X, and since X doesn't belong to itself, therefore we can say X belongs to itself by this rule of collection of all the sets. We say that X belongs to itself. Hence we have an ambiguity. Ambiguity means confusion. Hence we have an ambiguity in the inclusion of X. Therefore, we say that, or we state that, there is no set of all the sets. Now let's see the second proof. This is a proof for modify Russell paradox. Modify Russell paradox, MRP. Let's define a collection X as collection of all set A is a set such that A is an ordinary set. Let's define a collection X such that A is a set and A is an ordinary set. Here X is a collection of all the ordinary set. Now let X is a set. If X is an ordinary set, this implies X belongs to itself by the rule of why? By the rule for collection. Since X is a collection that contains all the set that are ordinary set, and since X is an ordinary set, it belongs to X itself. Therefore, X belongs to X by the rule for collection. This implies since X belongs to X, that is X belongs to itself, we say X is an extraordinary set. By the definition of extraordinary set, we say that X is an extraordinary set. By definition of extraordinary set. This implies X doesn't belongs to X by the rule for collection. By the rule for collection. Now, if X is an external set, this implies X doesn't belong to itself by the rule for collection. By the rule for collection. This further implies X is an ordinary set. By the definition of ordinary set, by the definition of ordinary set, then this further implies X belongs to itself by the rule of collection, by the rule for collection. Now we see that in each case we have ambiguity in the inclusion of X, of the element X in X. Therefore, we conclude that there is no set of all the ordinary set. Eighth, let's discuss an axiom. Two sets are equal if and only if they have the same elements. That is, set A is equal to set B if and only if X belongs to A implies and implies B implied by X belongs to B. Let's take an example for the above axiom. Let's define the set A as set of all X elementary natural numbers such that X less than 5. X is strictly less than 5. And let's define another set B as set of all X from n positive integer such that X is less than 5. And this set A in roster form is 1, 2, 3 and 4, and B is 1, 2, 3 and 4. Here we see that A and B are same set because they have same number of elements as well as all the elements are same. Therefore, these two sets are equal. And these two sets A and B are called as equal sets.